In the previous videos, we have discussed two applications of resultant. One is to determine whether or not two polynomials have a common root, and the other is to eliminate variables. The resultant of any two polynomials with respect to a variable t is not gonna contain t. Thus, in particular, if we have a parametric curve with parameter t, we can take resultant with respect to t to eliminate t from these equations and find a relationship involving only x and y. This also, of course, works for finding equations for parameterized varieties of higher dimension, not just a curve, but we'll need to take resultant several times. And for that purpose, it might be easier to use a Grosvenor spaces. Now in this video, we're gonna talk about the third and arguably the most exciting application of resultant. We'll talk about how resultant gives us information about intersection of plane curves. And we'll discuss the famous Bezout's theorem. To motivate the statement of the theorem, let me ask you this. So, can this be the graph of a polynomial of degree 5? Well, if you look at this carefully enough, you'll see that this graph has 7 x-intercepts, and that's not possible for a polynomial of degree 5 because a polynomial of degree 5 can have at most 5 roots. So a polynomial of degree 5 cannot intersect the x-axis at more than 5 points, and actually it cannot intersect any straight lines at more than 5 points for that matter. So we see that there is some relationship between degrees of two curves and the number of common points of intersection. Bezout's theorem tells us how to find the number of intersection points of two curves purely from the degree of the two curves. So what do you think is the relationship between the degrees of the two curves and their number of points of intersection? Well, if you look at these examples here, you see here we have a curve of degree 2 intersect a curve of degree 1 at 2 points. Two curves of degree 1 intersect at 1 point. Here two curves of degree 2 intersect at 4 points. So it's reasonable to conjecture that possibly two plane curves of degree m and n intersect at exactly m times n points. But that's clearly not quite right. For example, according to this, then a curve of degree 2 has to always intersect a curve of degree 1 at 2 points. But what about a situation like this? Well, actually, these two curves do intersect. It's just that their points of intersections are complex. So let us adjust this statement to account for complex point of intersections. So we'll say two complex plane curves of degree m and n intersect at m times n points. But that's still not quite right, because on the complex planes we might still have parallel lines, and these do not intersect. Well, they actually do, but at infinity. Thus, for our statement to be true, we need to look at projective plane curves instead. That is, we need to add to our affine plane a point at infinity for each direction. Then every two parallel lines will intersect, and actually every two curves will intersect. We're gonna see why that is. Okay, so we made some modification, but the statement is still not quite correct, because it's not true that any two complex projective plane curves of degree m and n are gonna intersect at m times n points. For example, here we have a curve of degree 2 and a curve of degree 1, but they have only 1 point of intersection. So what's going on here? Well, even though visually this looks like 1 point of intersection, we should in some sense think of it as 2 points, because this is the limit of these 2 points as this red line moves down here. So we would say that this is a point of intersection with multiplicity 2. If we think of this as the graph of the parabola y equals to x squared and this as the x coordinate, then the multiplicity of this intersection could be interpreted algebraically as the multiplicity of 0 as the root of this equation, which we obtain by setting these two equal to each other. So to account for this situation, we want to modify our conjecture and say instead that, okay, two plane curves of degree m and n are going to intersect at m times n points, but that's only if we count multiplicity. Now in this form, this is no longer a conjecture, it's actually a true theorem. In the next video, we're gonna use resultant to give an elementary proof of this theorem. In later videos, we're gonna give a more sophisticated formulation of this theorem, defining more precisely what multiplicity means. And then we'll give some alternative highbrow proofs.